All right, we want to introduce a key and important concept that we talk about with AC systems, which is what about the power flow that happens? And we're going to particularly talk about what I call single phase networks. Okay, let's go back to the original definition of power. So the definition that we learned in physics is that power is the rate at which energy or work, right? So the term that we sometimes use for energy is work, right? It's the rate at which energy or work is absorbed or sourced by an element. All right, so P of T by definition is the rate at which energy is used, which we write as dW dt, right? Because typically we talk about energy as work. All right, so you derived back at the very beginning of 2111 or in physics that if I had a charge with a particular voltage, the amount of energy that that charge has is however much charge it has, Q, and this is in coulombs, times whatever voltage it has. That's how much energy is basically in one charged particle. So the way we derive power is we say, well, that's the rate at which energy is used. So we say it's the rate of dV Q dt like that. All right. So if I think of a charge having a particular voltage V, and that voltage is constant, I can write this as V times dQ by dt. So if I have a charge with a particular voltage that is moving, this guy becomes V times I, okay? Because remember, dQ by dt is I. So essentially what we learned is that power, which is the rate at which energy is consumed, is equal to voltage times current, okay? So if I have a typical element like I have right here, and I'm following the passive sign convention, what I have is basically two conditions, right? Power, which is the rate at which energy is utilized. If power is positive, it means that energy is being absorbed by whatever element I have. And if power is negative, the element is sourcing or supplying energy to other systems, okay? So when power is positive, we say we have a load. So absorbing energy means that I have a load. And if my power is negative, I have a source, okay? It's important to remember this idea is that power is the rate at which energy is used, okay? Now in a DC circuit, that was pretty straightforward, right? In a DC circuit, let's say I've got a 100-watt light bulb, and that 100-watt light bulb is connected to a voltage source with 120 volts. So if I looked at V of T would be simply a constant value here at 120 volts. All right. So if my light bulb is rated at 100 watts, the current would be since power equals V I, if I have 100 watts and my voltage is 120 volts, my current I must be 100 divided by 120, or 0.833 amps, okay? The key thing is here, I of T is constant, V of T is constant, and so the power, P of T, is also constant, okay? DC circuits are pretty uninteresting in that regard. What about an AC circuit, okay? So let's say I've got this particular guy right here, right? So let's say I've got my 100-watt light bulb, just like I would in my house. I have a 100-watt light bulb connected to a voltage source, okay? So this would be like a single circuit in my house. In this case, what would I say? Well, typically we think of the light bulb as being like a resistor. So let's say instead of it being 100 watts, let's just say this particular guy has a resistance R, all right? And that is how you can think of a light bulb. So basically I just have a really simple circuit that looks like that, okay? So if I were to say what's the current look like, I just use Ohm's law, right? So I of T would basically be V of T divided by R, or I can say V peak divided by R times cosine omega t, so it looks the same as the voltage. In other words, it's in phase with the voltage. Sometimes I just write that as I peak times cosine omega t. Okay, like that. All right, so if that's the case, power by definition is voltage times current, right? So that would give us V peak times I peak times cosine squared of omega t. All right, this clearly is not constant. Now we're going to take a look at it here in a second in a particular example. All right, so we'll do like we did for the house. So I said V peak is about 169 volts. The RMS value is about 120, and if you did V peak divided by square root of 2 to get VRMS, you do it for these numbers, you'll see that's about correct. The frequency is about 60 hertz, so the radiant frequency is 2 pi 60 hertz, or about 377 radians per second. So if I run that, okay, here's what we get. All right, so this on the top here is the voltage I have. So I can see the peak value looks like it's about 169 volts, right? If you look at this, what's on the axes over here. And I see that the peak value in this particular case is a little bit more than an amp, all right? And what I've done is I've isolated one particular period, okay? So I'm looking at a period basically from the peak to the peak. And if I look at this, down here I have my power, P of t, which we said was V peak, I peak, cosine squared omega t, like that. If I look at what I have, as we said, the current and the voltage are basically in phase with each other. So the voltage being on top, current here, they're in phase with each other. One of the things I notice here about P of t is that P of t looks like it has twice the frequency of either the voltage or the current, right? When I say twice the frequency, because if I look at one period, which was marked out with these red lines, I can see that power goes through one period here and a second period here. In other words, it went through two variations. So in one period of the voltage, my power, P of t, went through two variations. So it would seem like what I have here is something that looks like it's varying at cosine 2 omega t. And in fact, one of the things I notice if I look here at what's on my y-axis, I see that the minimum value of P of t looks like it's at 0, and the maximum looks like it's at about 200. All right, not 2,000, 200, okay? So it looks like I have something which is offset. So it looks like P of t somehow has a offset, some constant, plus something that's varying with cosine 2 omega t somehow. All right. Now, it turns out that I can take a trig identity and I can show that V peak, I peak, cosine squared omega t actually turns out to be this. So I have a DC value or constant value plus something with twice the frequency, right? So we'll look at that again, right? So here it's zoomed in a little bit, right? When I'm zoomed in, here's one period of the voltage starting right here. Here's where that period ends. And what I can see is the power varies twice as I go through that. Now, I set this up assuming I was looking at a 100-watt light bulb, and I am. All right. The thing is, if I look at this, I see that I'm running through many different power values with this light bulb, not just one value. So when I have my DC system, I always had 100 watts going into that light bulb. But when I have my AC system, I see that the power is actually fluctuating or pulsating between 200 and 0. So why do we call it a 100-watt light bulb? Well, let's look kind of carefully at the waveform again. All right, so again, I've isolated one period here. And I'm showing in that one period, of course, that P of t pulsates. All right, in other words, it pulsates and fluctuates 2 times. So in one period, I see 1, 2 periods of the power. What I've brought in here is the average value. This is the average of P of t. And I see that that average value looks like it's at about 100 watts. So what's happening is I have this sort of variation around an average value. And that average value works out to be 100 watts for this 100-watt light bulb. So in AC systems, what always happens is that the power fluctuates twice over a period like we have right here. Okay? So if I have fluctuations happening twice over a single period, it becomes really difficult to talk about what is my power. So what we do is we define a new quantity here called the average or real power. So in AC systems, the average power delivered to the load is oftentimes what we talk about when we give a number that we associate with the load. By definition, the average value of the power is given the term capital P, and it's given basically just using the average of a function, right? So we've said before the average value, x average, would be 1 over t, integral 0 to t, x of t, dt. So P, the average power, is the average value of what we call P of t. This is sometimes called the instantaneous power. Instantaneous power. Okay. So power in an AC system is a function and it changes over time. So what we do is we define this average value. So if I look at the graph here, right, as I go over, in this case, so over one period of the voltage, I go through 2 periods of the power, but I can see that the average value of that looks like it's about 100 volts. So we call this a 100-watt light bulb because the average power that flows into it when connected to a 120 volt RMS source is basically 100 watts. Okay? Now, I call this term average power because it's the average of P of t. But the term that we use to refer to it is typically the real or active power. Okay? And it's the average amount of power transferred to the load over a single period.